Good morning, everyone.
Hey, Mr. Younger.
Yes.
Can I talk to you like 2 minutes about Lab Thursday?
Yeah.
I will not be able to make it. I will be in the hospital. So, is there like anything I need to do beforehand?
Let me see. The Thursday lab, where you could actually make it up if you wanted to. The following Friday, not the same Friday, but the next Friday, because that lab's like 1 week behind us. So if you want to make up for missing it, you can attend that one. It's at 1 o'clock on Friday. But you don't need to do anything. If you can download the lab material after it's posted and do it, you can at least get 50% of the credit for attendance by just doing it and turning it in on time.
All right, thank you.
No problem.
I also have a question about the third practice test. It
Go for
seems
it.
to still be locked.
Dang it. Okay, let me check that real quick then. Third practice test. I'm going to check it. That's not very helpful. I never locked the practice test. I don't understand why it's locked at all. It's weird. Okay, practice test 25 and 26. Oh. Yep, it's locked all right. I agree. No, we established that. Okay, it should be. Dang it! Why won't it? It should be available now. I don't know how that date even got in there. It was set up for August 9th or something stupid like that. So here we are.
Thank you.
No problem. Thank you for letting me know. There's a separate area where you can go to actually change that, and I evidently had left it there in that spot, not in the spot that I normally work with my test online. So it will. It's fixed now. I'm sorry. And that's on chapter 25 and 26, and we're doing 26. Where I'm going to do a problem from 25. I've already worked one that I thought was the more complicated, which I didn't give you all the details because it was right at the end of class, but I did work it out on the sheet, and it's just like the example, the last example in the back of the book, I mean, in the end of the chapter, where we were calculating the current density and then using that to calculate the drift velocity of the electrons in a conductor that's carrying a certain amount of current. So that's something that I think is sort of the more difficult one to work in this chapter. Another one is some of the ones that we do where we do some tricky little calculus type stuff. And I'm going to do that. And the rest of them I think are so trivial, there's not much need. And I mean, you can see the examples in the book, they're plenty good. So does anybody else have any questions before we get started on that? Okay, first I'm going to share a screen and show you something kind of cool. So this little bugger here is a strain gauge. And here's one like on a, you could think of this maybe as a shaft, propeller shaft, say for a cruise ship or something like that. When you actually are putting a shaft like that under torsion, which is what you're doing when you're, using propeller, then it tends to stretch and sort of twist a little bit. And the amount of twist you're getting on it is related to the force that it's being put under, in this case, the torque it's being put under. And you need to keep track of such things, because if you do too much, like you don't know there's something fouling your prop, for instance, then the shaft could break or any other crazy stuff like that. And then sometimes it's just a matter of all your calibrations are off and stuff like that. If that thing twists through a large enough angle, it could be sort of like what happens when you stretch a spring beyond its stretch point. It'll get sort of warped and then it won't come back. Same sort of thing can happen with metals when they're in torsion like this. So these strain gauges are super valuable, and really they're just basically electric circuits, but they're electric circuits with what we call a Wheatstone bridge. A Wheatstone bridge is basically, let me see if there's a picture of one. I bet you there's a picture of one of the Google search I did. Maybe not. Okay. A Wheatstone bridge is basically 4 resistors that make a diamond like this. So there's one here, one here, one here, one here. And then there's a resistance across here, and you balance it until the current through that middle, through that ammeter, is 0. But if you get it a little bit off, it can detect it quite a bit. So what they do is they build a circuit that way and make that wire the wire across that middle, the one that could be stretched. And if it's stretched a certain amount, then it can be determined by the change in resistance of the wire, which obviously changes the current and that sort of stuff. So that's really what we're talking about with these strain gauges. They use them to deflect, calculate or determine the deflection of a aircraft wing, all sorts of cool stuff like that. So it's really a valuable tool. I want to stop sharing now. And there's a common result we use, and I'm going to go ahead and show you the result, and then I'm going to show you how to derive it. So let me put it on my document cam. It turns out when you use the strain gauge, both of these spellings are acceptable, by the way. Okay, when you use the strain gauge, it turns out that the change in length over the initial length is equal to, approximately is equal to, the change in resistance over 2 times the initial resistance. Okay, and I'm going to show you that that's the case. So the formula we know of is R is equal to rho L over A. And of course, if we were talking about initially, we'd say R0 is equal to rho times L0 over A. What we're looking at here is a wire that can be represented by, say, this, where this is an area A, 0, and this is a length L0, like that. And it's subject to forces in opposite directions like this. Now, because of those forces pulling it, this thing will actually stretch, but if you assume the volume and density, say, are constant, then what happens is you basically get a wire that's now longer, but with a smaller cross-sectional area. That's the new A, and this is the new L, which is actually L0 plus, say, let's call it DL, because if we make it small enough, it could be differential, and that's something I'm going to make use of. Okay. So if we assume, like I said, the volume and density are constant, and I'm talking about density, not this resistivity here. The density is also given the symbol rho, so that I just want to make sure everybody understood that. And the radius of this is also used to be R or big R. I'm not considering that either. I'm talking about the resistance here. Okay. We know that the other resistance, R, is equal to rho L over A, and we know that the volume is actually equal to A times L. And if we say that's a constant, that's also equal to A0 times L0, which is V0. Or, yeah, so the volume at the end and the volume at the beginning are all the same. So what I'll do is I'll take R and I'll replace the A with basically V over L. So this will become rho L squared over V. See, if I just put V over L there, the L comes to the top, or V over L there, the L comes to the top and the V is in the bottom, so I get L squared over V. So now if I take the differential of that, I'd say dr is equal to rho over V. The resistivity of the metal is not going to change, the volume is not going to change. And that's equal to our times dl, or dl squared, which would be 2l dl. Okay, so I'm almost there, but what I need, remember, I want the delta R over R0. So now I can say, well, R over R0 should be just, or excuse me, dr over R0 should be just rho 2 rho L dl over V. And now I'm going to divide that by R0, which I know is this formula, but I'm going to replace it, of course, with a V over L0. So in this case, it's going to be rho L0 squared over V. And you can see that the rows are going to cancel out and the V's cancel out. So now I've got dr over r0, and I have that 2 that, you know, we're shooting for, so that's a good sign. I just got to keep plugging away and see what happens. So I've got now 2L, and actually I said D lowercase l there. This is D uppercase L. By the way, I did buy me some pins that actually erase, and just the red ones came in so far, but I'm going to use those pretty soon instead of having to do this every time. And I don't actually have to do it in time that you're in here, but I need to do it before I put it up on the notes. And I try to do the notes, put them up immediately after class. So that's why I've been doing it now. Yep, it looks like this note one's actually ruined now. So that's supposed to be a DL. Just remember that. Now I've got 2L DL. Yes, somebody have a question?
I was just saying, got it.
Gotcha. Okay. There's another student just came in. All right. So we're pretty close. Now I'm going to make use of something I already did over here. I'm going to say that the L is going to be L0 plus DL. And actually, again, that should have been D capital L there, times D capital L over L0 squared. So I'll keep plugging away. I'm going to distribute my 2 and DL, so I get 2 L0 DL plus 2 DL squared over L0 squared. Well, DL is supposed to be an infinitesimal change, and these things are really, really small, and their changes to length are really, really small. So it's not unreasonable to say that a second order DL squared is very close to 0. So I'm going to say this is approximately equal to 2L0 DL over L0 squared, which equals, of course, 2 DL over L0. So now I've got delta R, or excuse me, I've got DR, but I want to switch it from infinitesimal to just a delta. So now I've got DR over R0, or the delta R over R0 is equal to 2 delta L. Again, I'm switching the differential to just a regular change in over L0. And you can see that, lo and behold, delta L over L0 is in fact approximately equal to delta R over 2R0. QED. Any questions on that? So that's a typical type of problem you can do with this differential. I mean, with the R rho L, R equals rho L over A. Sometimes you treat it as a differential change in something, and then you can go back and convert it back and forth between a delta R and a DR. So doing that, you are able to show something that the industry understands about strain gauges. Basically, they often will use as a first order approximation, the strain is just the change in length over the length initially, which is just a change in resistance over 1/2, or excuse me, 1/2 of the change in resistance over the initial resistance. Okay. All right, so that was sort of, like I said, the last one I really want to show you about chapter 25. So we'll say now we have ended chapter 25 and we are entering chapter 26. And chapter 26 is just called DC circuits. And they start off with a nice little diagram asking you about headlights connected in series versus in parallel. And I'm actually going to do something similar to that myself. But before I do, I'm going to first just give you an intro to power, which is actually, I shouldn't say ended chapter 25 because I forgot I wanted to solve this power problem for you. Yeah, we'll say line through there. I lied. I just remembered I wanted to do this. Okay. We've got the winter coming up, and I guess hurricane season is technically over, but there's still a chance that we're going to be using generators in the near future to generate our electricity. So I thought I'd work a problem with that so you can understand what I meant by using power ratings to determine, you know, how big a wire to use, stuff like that. Well, the same problem happens when you buy, say, a generator. I went and bought a generator. Our last hurricane, we were without power for, I think, about 3 or 4 days. And really all I needed it to run was my refrigerator and freezer, because they're gonna, you know, that's where all my food is. But I wonder if I could run my actual oven on that, or my dryer. Obviously the dryer is not essential, but they're actually about the same amount of power. So what you can look for instance, you'll find something claiming to be a 13,000 watt generator. But when you read it, it'll say sort of a starting watch or a starting wattage or something like that. What the working wattage is actually 10,000. So in other words, it can handle a surge of up to 13,000 watts. So if you turn a microwave on real quick or something to get that extra 3,000 watts, a hair dryer, for instance, then it can handle that extra 3,000, but it's not going to do it very long. So what I was thinking about is how many amps can this device put out? So A, how many amps at 120 volts can this generator produce? So that's one question. Another question is, what if I was doing everything on 240? How many amps at 240 volts can be produced? So for instance, if you have a camper that maybe you're staying in or something like that, they have a single hookup and it's like a 30 amp supply or 40 amp supply, stuff like that. Could you run the whole camper? You know, if I had a camper in my backyard, it might be smarter to just let my crap go in the house and move out to the camper for a little while, because I can put the generator on the outside and live in a decent space, right? And we treat it like a vacation. Another question I want to answer is, can I run a dryer or stove? Let's say, can I run a, first off, let's say 746 kilowatt hour per year refrigerator and can I run a let's say approximately 5,000 watt oven, which is about the same wattage as a dryer as well. So, you know, obviously doing your laundry is not as important as eating and surviving, but those are some common questions. So let's start with part A. Well, basically P is equal to IV is our power equation. Remember, I showed you there's a couple other versions you can use. For instance, P equals IV. I can replace V with IR and then you get I squared R. Or I could replace I with V over R and I get V squared over R. Those are all equivalent forms of power. In this case, I want to know a current. I know a voltage and I know a power, so P equals IV is just fine. In fact, it gives me I is equal to P over V. So I'll take the working power, which is 10,000 watts, and I'll divide it by 120 volts. And when I do that, I will get 85. I think it was 8. No, yeah, I think it was. Oh yeah, no, that was something. It's 83.33. Y'all can check this with your calculator, of course. 83.33 amps. So that's a pretty significant amperage, and I'm only using 3 sig figs, so I should put an underline on that one. And obviously, part B, if you're running at 240, then I is equal to 10,000 volts, or excuse me, watts over 240 volts. That should be, of course, half as big. And sure enough, it turns out to be 41.66 6, 7. Again, 3 sig figs is really all we're looking for here. So we can get out 40 amps at 240. I just recently acquired a camper and it runs on 30 amps. So I could literally just plug my camper into it and everything will work just fine. So, and the next step up was a 40 amp supply. So this would probably even work for a 40 amp, even though it doesn't give me much margin for error. I would rather have something that's capable of pushing, 45 or 50 amps to use for a 40 amp service. But anyways, that's that. So part C, what I want to know is, can I run a 746 kilowatt hour per year refrigerator? So they gave you some data there. And what you really want to think about is, what did they give me? Well, they said it was 746 kilowatts per year. It's a 5-star energy rating, blah, 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 all this good stuff. Well, 746 kilowatt hours per year is an actual unit that we can work with. So I can find out what its actual power is. And notice it says kilowatt hour. That literally means watts times hours, which hours is a unit of time, and watts a unit of power, which is work divided by time. So if I really want the total amount of work done, I can multiply kilowatts times hours and get a measure of the total amount of energy, right? But what I want to do is figure out how many watts this thing is. So I want to get rid of this H per year dealio, okay? So I can say, for instance, that 1 year is equal to 365 days. And then I can say that 1 day is equal to 24 hours. And you'll see what happens. Now I've gotten rid of the year with that one. I've gotten rid of the day with that one. And now I've gotten rid of the hours with this one. So really, I'm going to say 746,000. That's to get rid of the kilo, okay? Times, and this will be watts, times, divided by 365 times 24. So just ignore that. When I actually do that math, I get about 85 point, let's do it so I don't give you the wrong number. $85.1598. Watts. Okay. So this is again a 3 sig fig thing, roughly. So I should probably say all these are rounded, but since that was a 5 there, I wanted to make sure everybody knew what was after the 5. And I couldn't really round it there because that would make that a 6. So anyways, I had to show all 3 of them. So that's really the answers that we've gotten so far. We can run 83.3 amps at 120. We can run about almost 42 amps at 240. And we see that this refrigerator is actually only going to use about 85 watts. So you don't even have to calculate current for that. You just have to compare it to that figure. So taking out 85 watts, maybe round it up to 100 to be safe. All right. So now we got 9,900 watts left. So let's check part D, which is, can we run a 5,000 watt oven? Well, again, this is actually given to you in watts. So all I got to do is subtract that. So if I want to run a refrigerator and my oven, my refrigerator maybe takes 100 watts and my oven takes 5,000. So I subtract 5,100 from this and I got like 4,900. So yes, I can. And yes, I can. That's it. That's some of the everyday math that you just need to know as a human, that's going to ultimately probably own a house and stuff like that, or even, at least rent a house where you might be wise enough to have yourself a generator so you don't get stuck without power for too terribly long. I went without power. The longest I ever went was we had just left Greenville, North Carolina. I had started my PhD program at Chapel Hill. And I left Greenville, North Carolina, and the dang hurricane went through Greenville and tore it all to pieces. By the time I got to Chapel Hill, I slept through it. I'm normally a worry ward about such things. Even though I knew structurally everything was fine, I just like to, be safe. So I'm sitting there and I'm like, man, this is nothing. This is the whiskiest storm ever. I fall asleep. I wake up the next morning and like the power's out and it stays out for like 2.5 weeks. They're just not used to that kind of wind in Chapel Hill. Sadly, that was the one that destroyed Greenville, though. We actually, a couple weeks later, ended up, even though our campus had lost a lot of the housing for the students, we ended up beating University of Miami, which was ranked like #3 in the nation at the time. And our football team beat them. So that was cool. All right. So now this really ended chapter 25. Seriously. Okay. So we're done with that one. It's in the books. All right. So now chapter 26, like I said, is DC circuits. And really the crux of what you're going to try to learn in this chapter is really being able to work out circuits. So I can give you a circuit diagram, and ideally what that means is you're going to be able to take that circuit diagram and tell me what the current is and the voltage is through what current is through each item in it and what the voltage is across each item in it. And we're going to, sort of start off doing something that looks kind of weird and not very algorithmic or helpful. But then I'll give you a set of rules that you'll do, and then it makes it pretty clear. Then the only difficulty is you have to solve a system of equations. So if there's 3 separate currents, you're going to have to solve 3 equations, 3 unknowns, and that's usually about as high as I go. Sometimes I'll give you 4 currents and 4 equations, but very seldom do I do that. Okay. So first off, I want to talk to you about batteries. So the way we look at batteries is I told you about how we make them. You can just put 2 dissimilar metals in an ionic solution and touch one of the metals and make that the anode and the other one the cathode, and then you have a power source. Well, over time, that battery is going to lose oomph, right? And really, it's all sorts of things going on. But for instance, to give you an idea, the circuit that you could do, for instance, to gold plate something is exactly a battery. Okay, so when you are doing a gold plating process, you basically have one of the metals is gold and the other metal is something cheap and easy to make or easy to buy or whatever. And then you put it in this ionic solution and you run current through it. And what you see is over time, the little pieces of gold will end up on top of the other metal. And you've then gold plated it. But in doing so, I think you can realize over time, you're going to run out of the ability to produce more gold on that. Right. So that's sort of the same thing that happens with a battery. So when you think about it that way, you can say, oh, okay, well, how will we actually model that? Well, the way we model it is we assume that the battery has an internal resistance and that internal resistance actually grows over time. And it's sort of true. I mean, a battery actually does have an internal resistance. You can tell that because it initially, when you buy a AA or AAA battery, it'll read like 1.72 volts, just not hooked up to anything. And then you use it for, several hours or whatever, and then you connect it and it's more like 1.6. And if you do it even more, it might even drop down to 1.49, right? So that's equivalent to having a resistance. So the way we draw a real battery is we'll do something along these lines. We'll say, all right, here's our pile, and it has an EMF, electromotive force, equal to say, let's say 6.00 volts. And let's say it also has a internal resistance R equal to 0.75 ohms. And this point, this is the positive terminal of the battery, and this is the negative terminal of the battery. So we're picturing this all as if it's inside the battery. Now we can connect that to some load. Let's say the load has a resistance of R equals 100.0 ohms. Okay. So that's how we model it. And then we just got to figure out some stuff. So for instance, I would like to know what is the terminal voltage, V terminal, which is really the voltage at the plus minus the voltage at the minus. Okay. That's one of the things I want. I'll call that A. One of the other things I want B is the current going around the circuit. So there's going to be a current established going this way. I want to know what that is. And then C, I want to know the power lost due to R, the internal resistance. Okay, so these are very typical problems. Well, you can think about it sort of like I told you when we think about batteries, there are things that lift sort of the charges up. You can think about voltage as a height. So you're at zero height, zero height. In fact, everywhere from here on, you're at zero height, zero height, zero height, zero height, zero height, zero height. Then you get right here and you climb up like 6 meters. So right here is 6 meters. Okay. And then you go 6 meters, 6 meters, 6 meters, 6 meters, because we're assuming the resistance of the wire is essentially 0. And then boom, you hit this part and you have to step down to some lower voltage. Well, what is that voltage? Well, it turns out that that voltage is the terminal voltage, because I said this is 0 over here. So V plus minus V minus is actually got to be the voltage here. So that says V terminal is actually the voltage of the battery, which we call the EMF. And then Ohm's law tells us that the voltage drop across any resistance is IR. So that's going to be minus I times little r. So that really is what the voltage is here. So that's what a bubble would give us, you know. And remember when I say a bubble, that's when I'm poking the red probe from the voltmeter or multimeter. I'm poking it at that spot that the bubble's attached, and the black one's over here at the ground, which is normally the low side of the battery. Okay, you can actually put it anywhere in the circuit you want, but I almost always do it at the low side of the battery if you got one. Okay, so really to do this, I've got that, but I don't have I yet. But what I do know is that basically this resistance drop and this resistance drop are going to get me back to 0. So I do know that V, or E, I should say, is actually equal to, notice the current doesn't have any other path. Every little electron, say, that goes through here has to also go through here. So the currents of these things must be the same. So this voltage must be I times little r plus I times big R. So that tells me I is just going to be E over little r plus big R. Well, E is 6.00 volts and little r is 0.75 and big R is 100.0 volts. So 100 plus 0.75 gives you 100.75, but you really only allowed the 7 as a decimal place. So that actually gives you 4 sig figs divided 3 by 4 sig figs gives you basically the 3 sig figs is all you get out. So with this answer, all we have to do is take the 6 volts and divide it by 100.75. And when I did that, I get 0.05953 amps. Now, again, I said we only can have 3 sig figs. This one's just a placeholder. So 1, 2, 3 sig figs. These two are extra, and I kept them because obviously that's a 5, and I always got to keep a 5 so you'll know that it wasn't rounded up already or something. Okay. Now, another way of writing this is really convenient. Is you'd say this is 59.553 milliamps. Okay. So actually, I got B before I got A. So I'm going to go ahead and write down, circle this, and put a B next to it. And now I can go back and get A. The V terminal is just 6.00 volts minus 0.059553 amps times 0.75 ohms. Obviously, this is only going to be 2 sig figs. And in fact, when you do that, you get 0.044665. That's what you get when you multiply those two numbers. That means 2 sig figs only gets you those decimal places. And then I've got 600. Notice the 4 does line up with the last digit of the 6.00. I said 600. Sorry about that. But notice that 4 does line up with that. So we get 3 sig figs from this. So I'm actually going to do 6.00 minus the 0.44, and that's going to be 5.9553. So I actually only can keep this digit, and these are extra, and that's volts. So that's part B. See, or that's part A, sorry about that. So you can see that this is in fact, since that doesn't look that good, this is in fact very close to the 6 volts, right? 5.96 is pretty darn close. So that's not too bad. That's exactly the way we expect things to happen. Now, over time, if you let the circuit run for a couple hours, you'd probably come back here and find that this resistance is now, 1.5 ohms or something like that. And then this is even smaller. Maybe it'll be 5.91 volts. And that's just what happens over time. Now, the last thing we want to calculate is what is the P loss due to the internal resistance. In other words, there's some power loss, P equals IV for everything in here. So there's a power loss for that one and for that one. But we want to know in part C, what is the power loss for R? So I'm just going to say P sub little r. I know the I because the same I that goes through everything is this one. And I know the R, and I don't have to calculate it. So I'm going to use the P equals I squared R version. And that I squared is 0.059553. Actually, those two are bad. Amps, that's going to be squared, times the resistance, which is 0.75 ohms. So that's going to force us to only have 2 sig figs. When I carry out that calculation, I get 0.0027 watts. And that is the power lost by the internal resistance. You can tell if you did for the other resistance, that's going to be 100 times that number instead of 0.75. So the power loss is majorly coming from this, not really from that, but there is some. Okay. Any questions on that? Everybody understand how that worked out?
Yep.
Now we kind of did something there. I argued that basically E is equal to I times R plus I times big R, right? And that means in reality, you could actually say, hey, did Mr. Younger just tell us that I times R plus R was what E was equal to? That's an actual conclusion that we reach from common sense. So now I'm going to make that a little more formal. So let's take a circuit with a battery. And let's have a resistance R1 and a resistance R2. And actually, you could have any number of resistances. I'm just going to make them all in series. Okay. But I'm just going to do 2 because you can tell I just added a plus and a dot, dot, dot after that if I want to do more. I'm going to say this is a voltage V. And I'm going to say it's going to create a current I like that. And I want to find an equivalent circuit where still we have that same battery of voltage V and we still have that same current I leaving. And we replace it with one resistance that we'll call R equivalent. And it's actually R equivalent for series, so I'll put a little S on it for just right now. Okay. Well, what I do know is that the voltage lift here, because I'm going to go from 0 to some height V here, and it's going to stay V, stay V, stay V, stay V, stay V, and then it's going to start to go down. It's going to go some distance down. We don't know what that distance is. And then it's going to stay that voltage, stay that voltage, stay that voltage, and then it's going to go the rest of the distance down. So what we know is that V is equal to V1 plus V2. And again, if it was multiple resistances, we just have plus dot, 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 right? Now, Ohm's law also tells us that V is equal to IR. So we can say I times R equivalent for series is equal to, notice it's all the same current. There's no other paths for this to go through. So every little electron that say leaves this side has to go through R2 and has to go through R1. And if you do that for 1 minute, then you've got a current because you're taking the number of coulombs and dividing it by the seconds, 60 seconds, okay? So here I've got I times R1 plus I times R2, and again, plus ... for any number that you had. You can see though that the I's cancel out because they're all equal. So R equivalent for series is just equal to R1 plus R2 plus ... for however many resistances you have. And notice that's the series formula. That is an equation that's numbered in your book, so it's one that you can use. Okay, so now let's consider another scenario. What if we had 2 or more resistances in parallel? We've learned a little bit about this from doing our lab, so we're actually probably a little better off than had we not done the lab already. So I think some of this should seem a little bit more common sense than it normally would for students. But if you come out here and you take and go to some resistance here, and we'll call that R1, and you come up here and you do another resistance, you call that R2, and ... You can have any number of resistances you want. This is again going to be V. This is going to be I, but I'm going to have to label this one I1 and this one I2 and all the other ones I3, I4, I6, I7, whatever, right? Now, if it was just 2 though, let's think for a second. Let's say 100 amps is what came out. And let's say 20 went into R1. Do you know how many have to go into R2 if that's the only 2 of them? So 100 came out, 20 went through R1, and if we pretend that's the only 2, how many must go through R2?
80.
80, right. And that's just conservation of charge. It should make sense, right? We can't just create and destroy electrons. So if 20 of them go through here, then the other 80's got to go through here. And that's the net effect, is that basically I is equal to I1 plus I2 plus ... But again, we have V is equal to IR. So I is equal to V over R. So we can put V over R equivalent, and this one's going to be parallel. And we're imagining now a circuit like this with a single resistance R equivalent parallel right there. The same I going out of it and the same V being there. So that's what this is, V over R equivalent. Well, that's equal to the same V over R1 plus the same V over R2 plus ... Why are these the same V? Have y'all discovered anything about this before? In your labs or otherwise?
Yeah, we used that equation in the last lab, didn't we?
Yes. In fact, you discovered it because what you did was you measured the voltage across each resistor in series, in parallel, and you
Right.
found that V1 is equal to V2 is equal to V3 is equal to the voltage of the battery. And then when you did it in series, you found that V1 plus V2 plus however many you had was equal to V. So we already knew these from the lab, just like we already knew this from the lab. Okay. Now, since all those are equal, we now get that 1 over R equivalent, and I'll put the parallel on it because we're got 2 on the page here, is equal to 1 over R1 plus 1 over R2 plus ... And that's the general formula. Okay, again, that's another numbered equation in your book, so that's one you can use. You don't have to just derive it every time. You can use it, and they expect you to use it. Now, the net result of this, notice this is exactly the opposite of what capacitors had. So in capacitor, 1 over C equivalent in series is equal to 1 over C1 plus 1 over C2 plus ... And C equivalent was equal to, and this is parallel, C1 plus C2 plus ... So remember, these are exactly the opposite, but the conclusions we reached are the same, just for the opposite objects. In other words, the total resistance of the resistances in series is the sum of all of them. It's bigger than any of them, of course, but it's literally as big as the sum of all of them. And the resistances in parallel, the net resistance of them is less than any one of those resistances. So if this one was 100 and this one was 50, we'd know it'd have to be less than 50. Okay, that's what that formula tells us. So now we have some rules where we can deal with certain types of circuits. So what I want to do now is let's work an actual circuit out. Okay, so I'm going to make up a resistive circuit. Let's say I have a voltage here. It's going to go out into a resistance R1 equals 100 ohms. I'm going to assume all these have 3 sig figs, by the way. And then that's going to break up into R2 equals 200 ohms. R3 equals 300 ohms. And R4 equals 400 ohms. And then we'll go into, let's say, R5 equals 500. R6 equals 600. And R7 equals 700 ohms. Okay. So what we want to do is find a single resistance we can replace all these suckers with. What we're assuming is this is a voltage V and this is a current I. So what I'll do is start with the 2 or more resistors that I can easily deal with. I can't really easily deal with these 2 because I got a third one on there. So I'm immediately thinking these 2 right here are the 2 first ones I can make sense of. So I'm going to write this circuit as an equivalent to it. So I'm going to say now this part is just going to become a resistance right here in parallel with the 500 ohms one right there. In other words, the rest of the circuit's the same, but I want to find out what this is. Well, we know what this is. This is going to be equal to, since they're in series, this is going to be 600 plus 700. So obviously that's 1300 ohms. Okay. Now I'm going to make that equivalent to just a single resistance there and that. So I'm getting rid of these 2 parallel ones. So I know this is 1 over 1300 plus 1 over 500 is equal to 1 over R. Well, 1300 and 500 are not that easy to deal with. You could just go ahead and multiply them. I'll do that. So if I multiply this by 500, that's going to be 5 times 3 be 50, 65. 65 followed by 4 zeros. So this would be 65,000. And that would be 500. And this one I'm going to multiply by 1300. So that'd be 1300 over 65 followed by 4 zeros is equal to 1 over R equivalent. So I can now see that's 1800 over 650,000 is equal to 1 over R. So I can do R is equal to 650,000 divided by 1800. And I got 361.1 ohms. Okay, so now I've reduced all this to just a single resistor. Now I can take this bank right here and convert that. So I'm going to say this circuit is still equivalent to, now I'm going to show the battery and this little guy, but it's going to be equivalent to one resistance that I'm putting right there, and then the 361.1 ohms right there. That's what my circuit is now. So these are all in parallel. So I'm going to say 1 over 200 plus 1 over 300 plus 1 over 400 is equal to 1 over R. Okay. Now 200 goes into 400, but 300 doesn't. So I'm going to try 400, then I'll try 800, and then I'll finally get to 1200, and everything goes into there. So I've got to multiply this by 3 to get 1200. So this is going to become, to get 1200, I got to multiply this by 6. So it'll be 6 plus, I got to multiply this by 4 plus, I got to multiply this by 3. All that over 1200 is equal to 1 over R. So R is equal to 1200 divided by 13. One, 2, 0, 0 divided by 13. And I'm trying to do this without, using my calculator very much. So I'm gonna call that 92.31 ohms roughly. Okay. So now I can say this one's going to be 92.31 ohms. Now I can add all these because they're all in series and get the fully equivalent circuit. And it's going to be, in fact, 92.301 or 07 plus 361 plus 100. And that's going to give me 553.42. 553.42 ohms. And I'm just going to call that a nice even 553. So R equivalent is equal to 553 ohms. Let's go back and look at what we did and see what we got. Notice this one, we had two parallel ones. So as we thought we're basically going to just get the sum of the two, which is 1300. But notice here we had a 1300 in parallel with a 500, and we did, as advertised, get a value that's less than even the smallest one. So we got a resistance less than 500. Then I did these three, 200, 300, and 400, and in fact I got a resistance that's less than 100, much less than 200. So you can see when they're in parallel, the resistances make a smaller net resistance. Any questions on that? How's the images look today? Are y'all able to read the equations a little better?
A little better actually today.
Yeah, I bought a 50-foot Ethernet cable. Ran it straight to my Wi-Fi router. So hopefully that I was hoping that would work. All right, so that's another somewhat complex example, or very typical of this type of chapter. But like I said, that's sort of rigging and rolling. I could go back now and actually determine what the current is here. For instance, all I have to do is take this voltage, whatever it was, and divide it by this resistance, and that would tell me how much current is leaving here. And if you look at the original circuit, the current that's leaving here is the same as the current that's going through that. So I already know the current through R1, and I can already multiply that by R1 to get the voltage across it. And then if this was 100 volts, say, and this was 10, then it'd be 90 volts reaching here. So I know that 90 volts is the difference across here to all the way back to here, really. But then I have the current going into here, and I know that basically the current's going to divide itself so that the biggest part of the current goes through the smallest resistance. So if the current was, say, 20 amps, then most of that 20 amps will go through the 200, a little less will go through the 300, and a lot less will go through the 400. But the three have to add up to give you that. Once I got those individual currents, then I can multiply that current by R2 to get the voltage across it, and that current by R3 to get the voltage across it, and that current by R4 to get the voltage across that. And lo and behold, you get all three of them having the same voltage. So now you go from 80 to 80 minus whatever that voltage is, and that's the whole voltage across here. Then you say, well, the equivalent resistance here, if you divide that voltage by the 1300, you'll get the current through this one. And then if you divide that voltage by 500, you'll get the current through this one. So now I know the voltages across this one, and this one. And of course, this is going to be the current that left. So it'll have to add up. These two will add up to give you that exact same current that left. So that's all you have to do to analyze this circuit. So if you guys want to do this, I will allow this for an extra credit. And this is going to be 100 on conceptual. So basically, if I told you in the syllabus that I was going to drop your single lowest conceptual homework score, if you do this, I'm now going to drop your two lowest. Okay, that's how that will work. So what I'm saying to do that for extra credit is I want V1, I want I want V2, V3, V4, I want I2, I3, and I4. And then I want V6, V7, V5, and I6, I7, and I5. Some of these are equal, the same thing too. So don't think that they all have to be different answers. I5 as well. Okay.
And so is this still through mastering, or this we have to
You do it on a piece of paper
and then turn it into Canvas, or?
Yeah, I'll put an
Okay.
extra credit link in this week's module, and you can upload a PDF. So what you do is take a photograph of it, insert it in a Word if you want, and then convert it to a PDF. Or you might use, I use a Pro Scan, and that automatically takes my photos and turns them into PDFs. So just try to write legibly. If it looks really messy, like you ended up working all in circles and stuff like that, then recopy it in a more nuanced way, and that way I can give you full credit for extra credit. Okay. And you know, you can go back and watch this video. It's going to be up probably, it'll probably be up in about 4 hours. So when that's up, you can go back and watch exactly what I told you. I told everybody, you know, take this equivalent resistance and divide it into the voltage here. I will take V equal to 100 here, volts. And that's going to be what you use. So V equals 100, you're going to take 100 divided by that. That'll give you I. And then I is the same thing as I1. And then I2, I3, and I4 are going to have to add up to give you I1. But I times R2 and I times R3 and I times R4 is all going to be adding up to the same voltage, V2, V3, V4, because they're all the same, because they're in parallel. That's not kind of stuff. So I told you how to walk through that. So go back and watch this part if you want. We're only, what, 58 minutes into class. So you can fast forward, say, to the 50-minute mark if you need. All right, so that's another neat problem. Now what we're going to do is I'm going to examine a conceptual problem, two different conceptual problems really, but one I'm going to do to actually get the work, to get the actual numbers. The other ones I'm just going to do conceptually. So what we're going to do is we're going to imagine a battery, car battery, if you will. There's your plus terminal, there's your minus terminal. And you've got two ways of connecting this. You can connect it to a headlight in parallel like this. Or you can connect it in series like this. Okay. each of these have a resistance R. And obviously they're going to change as current goes through them. And, if one current's bigger than the other one, that's going to make a different resistance, all sorts of stuff like that. We're sort of ignoring all those details and just assuming they're going to behave like a constant resistance. But the real thing we want to know is which way gives you the most light. Okay. And the light really is proportional to the power. If they're fluorescent, then the power is almost 100%. The light that's put out. If they're incandescent, meaning like a tungsten wire that gets hot, then probably about 90% of it's just heat and the other 10% is actual light. But either way, the power that's dissipated through it is better. Is the higher it is, the brighter the light is. Let's put it that way. So if I look at this one, I can say, well, wait a second, with this one, I've got 1 over R equivalent is equal to 1 over R plus 1 over R, which is 2 over R. So R equivalent for this one is equal to R over 2. Okay. Now I need the power, and this is just going to be some voltage V. That's all we need. You don't need numbers with this. This is going to be a power now is equal to, say, I times V. You could use I squared R, so on and so forth, all sorts of stuff you could do. But you could use IV or one of those. But what I need to do now is figure out what's the current. Well, the current is going to be equal to V over R equivalent. So that's going to be V over R over 2, which is 2V over R. So now I can see that I'm going to get 2V over R times V, which equals 2V squared over R. That's how much power one of those lights is going to do. The other one, of course, will make it the same amount. So you'll get 4V squared over R. So total light is proportional to 4V squared over R. Okay. And this will be example 5. Now let's do this one. In this case, R equivalent is equal to R plus R, which is equal to 2R. I is equal to V over 2R, which is just 1/2 V over R. Then P is equal to IV is equal to 1/2 V over R times V. So when you add these two, you're going to get total light is proportional to, actually it's just proportional to V squared over R. Okay, because 2 times 1/2 gives you 1. So you can see this is actually going to be 4 times as much light when you put it in parallel. And in fact, that's the way headlights are wired in a car. And that's the way your light receptacles are wired in your house. For instance, I've talked to you about before about having the short slot and the fat slot and then the mouth like that. So one of these is basically hot, the other one's neutral. And if you have another one over here, the way you're going to run that wire is you're going to take the wire from this one, you're going to attach it here. You're going to take the wire from this one and you're going to attach it here. And then any other ones are going to do the same thing. So you can see that this wire is like this and this wire is like that. And those are the two basically the prongs. This other one's just, like I said, it's literally connected to a clamp on a pole that's 8 feet long stuck in the ground. Okay, all of those are connected and none that. So yeah, that's how they connect power. And you can even see when you actually look at a light receptacle. By the way, don't look at it when they're hooked up, because it's really tempting when you see the light receptacle sitting in there and it looks like this, right? It's so natural to just grab it right here, put your finger right there and your thumb right there, just so natural to grab it right. That's exactly where they put them darn wires. So it will light you up if you do that. So just look at one in the store, okay? One that's actually on the shelf for sale. What you'll see is there's a screw right here, and like that one's like gold, and then there's a screw over here, and that one's like silver. And there's got like a green little screw down here, and that's for the ground that goes to that. They also have holes in the back, and they've got little notches on the back that show you how far you're supposed to clip the wire to stick them in the hole instead of to do that. You can wrap 2 of them around here if you need, or you can do 1 in the hole and 1 in the here. All sorts of neat little things about light receptacles. But anyways, that's how that works. So yes, the parallel sort is much better. And another reason that the parallel sort is much better, remember a typical light bulb has that canister, the outsides of which is basically, say, the positive, and then it's got some insulator, and then it's got that little nipple, and that's like the negative. Well, the nipple never touches that, goes into a piece of wire, and that piece of wire then touches the gold thing. When a light bulb burns out, that literally means this wire melted in 2. But you can see, if this wire goes into here and then melts in half, then that's open the circuit and the other light bulb's not going to work. So that's the other reason in parallel. If this light bulb goes out, so what? The other one's going to work just fine. Okay. That's the way old Christmas tree lights used to be too, is all in series. So when one of them went out, they all went out. They've started wiring them a little better now, but they're still not perfect because they still got some where if one goes out, like 6 or 7 will go out. So that's kind of a weird thing. Anyway, so that's a good example. Now let's look at one with actual numbers. So let's imagine 120 volts. It's actually going to be what I'm imagining here is AC power. Okay. But remember, we learned at the end of last section that as long as you use root mean square or peak to peak, the formulas still work as long as you stick to everything. But when we use root mean square, the formulas are exactly the same. P equals IV, P equals V squared over R, P equals I squared R, that sort of thing. So we're just going to work with it as if it's DC, even though we really know it's AC. What we're going to have here is a 50-watt light bulb. And we can assume 3 sig figs on everything. And then we'll have a 100-watt light bulb. Okay. The other option, though, is 120 volts. 50 watts, again, 3 sig figs, 100 watts, like that, okay? So what we want to do is actually put our money where our mouth is. Let's look at these numbers and see if they work out like they're supposed to up here and so on and so forth. So first off, if I take this one, what I got to do is I first got to find out what the resistance is. And I immediately know that, notice the 50-watt light bulb, because they're in parallel, has 50 watts at 120 volts. That's what the rating means. So when you buy a light bulb that says it's a 50-watt light bulb, they mean it puts out 50 watts of power if it's connected to 120. So we know this is going to do exactly 50 watts. Similarly, we know 100 is also at 120. So P equals 50 watts for this one, and P equals 100 watts for this one. Easy peasy, no problem. Okay. You can work it out if you want. You can say, okay, well, let's see. P 50 equals I squared R would mean that would mean that, well, actually, I don't want to do it that way. What I can do, though, is I can say R equivalent is 1 over 100 plus 1 over 50. Obviously, that's 3 over 100 because I multiply this by 2 to get 100 there, and now 2 plus 1 is 3. So R equivalent is 33.333 ohms. And then if I divide 120 by basically 1/3, which is what that is, okay. Now I use V equals IR to determine that I is equal to 120 divided by parentheses 3 divided by 100. And obviously you're gonna get 4,000. Amps. Oh, excuse me. Supposed to divide it by 100 divided by 3. Excuse me. That was bad. Notice this is supposed to be over there because when I divide it by 100, it should be 0.003. I forgot to flip that over completely. It's 0.0 tens, hundreds, so that'd be 300 ohms. That's the resistance. Sorry about that. So now when I do this, I get I is equal to, I'm going to draw this line to separate the parallel from that. I is 120 volts divided by 0.0300. You're still going to get a pretty high resistance. I did that wrong too. Huh. I hate it when I go off script. You can see what happens when I go off script. I did get this for 3/100, and that seems right because this would become 2/100. 2/100 plus 1/100 is 3/100. So flipping it over should be 100 divided by 3. Yes. So R equivalent would be 100 divided by 3. And that is the 33.3 I got before. Y'all weren't helping me at all. Okay, so that was clearly okay. This was not so okay. Now I'm going to do 120 divided by 33.3. The currents were making way too big. That's why I knew I was doing something wrong. Divided by 33.33. And now I get 3.6. That makes a lot more sense. So I is equal to 3.6 amps. So now I know how much amperage is going through there. And I could actually find out the individual resistance of the resistors. So that's something we could do. Actually, damn it. Y'all see, did y'all see why I'm having these problems to begin with? Anybody see what I did? Like a very stupid person. Oh. I looked exactly at that circuit and notice how I labeled the resistors, the light bulbs. What did I label them with? What numbers?
100. Wait.
Yeah, I did watts instead of ohms. Like
what? Oh my gosh!
I can't believe I sat here and did.
I thought I was looking at like a weird way to write like a weird. I thought it was an artifact of like the low resolution, but
no, it's really bad. Your instructor seems to have had a stroke. And this is why I don't want to go off script. Seems to have had a stroke. So ignore that work. Okay, just ignore it. That's a complete screw up. Okay. We were right with this. This is exactly true because they're in parallel. We have 120 volts. That means this 50-watt light bulb is acting just like it's supposed to, and this 100-watt light bulb is acting just like it's supposed to. So this part is correct. So don't worry about that. That's good. Where I went wrong was when I just started treating watts because I told you guys that you should put your units down. That's exactly why. If I would have put a unit watt down there, I would like to think I would thought ahead and realize, no, I'm not doing the right thing, but I didn't because I just wrote down the number and I just ran with it. So all this is just crap. So what I was actually trying to do was show you that the resistance of these light bulbs, this 100-watt one, puts out more power. And the reason it does is because its resistance is actually going to be lower. So let's look at that. I can say the power of a 50-watt light bulb is supposed to be I squared R, but I can also say it's IV, and I can also say it's V squared over R. Okay. Well, I know V and I know P and I want to know R. So that's our best bet. So here's the right work, and I'll put it in purple so it won't be so confusing which is right. Correct is in purple, unless I make another mistake, is in purple. And now, of course, the purple markers will stop working. So I'm going to say P of the 50 watt. Yep, that's exactly what's happening. Purple's going dead. P of the 50 watt is equal to V squared over R. So R is equal to V squared over P. Well, R50 is going to be equal to 120 volts squared divided by 50 watts. Okay, and remember, a watt is a joule per second and a volt is a joule per coulomb, so that's going to come in handy. So I do 120 squared, which we should be able to do in our head, and then I'm going to divide that by 50, and lo and behold, I get 288. And notice that would be joules squared per coulomb squared for the volt, because the volt's a joule per coulomb, and then that's divided by watts, which is a joule per second in the bottom, so that becomes a second over joules. Notice what happens. You end up getting one of the joules canceling out, leaving a joule there. A joule times a second, or a joule over a coulomb squared. So you can see this is actually from V equals IR. You can see the resistance would have units of joules per coulomb per second. And you can see that exactly, coulomb per second. Say this joule up here is going to be one of the joules that I'm going to use, joule per coulomb. So that takes care of one of the J's and one of the C's. And then I'm going to take this and put it in the denominator in the bottom, which is, it's actually in the numerator in the bottom right now, the C is. So that works fine. I need that C there. And I can pull this C as a denominator down there, and I get coulombs per second, which is exactly what we got. Okay. So that joule per coulomb per second is exactly what the ohm is. So I just want to make sure you knew that that unit was right. Now the R is 100 is the same thing. 120 volts squared divided by 100 though. Now that we've worked out the nasty details of those units, we can trust it. And we see that this is going to be 144 ohms. Okay. So those are two values that we need to make sure. So you can see that the resistance of the 100 ohm resistor or the 100 ohm light bulb is actually smaller than the resistance of the 50 watt. So 50 was 288 and the 100 was 144. And in fact, they're exactly a factor of 2 different. So because of that, we can now see, oh, well, yeah, if I want to calculate the power, then power is equal to V squared over R would work, or you could use IV, but you'd have to know the voltage across it, which is cool. And you have to know the current through it, which we haven't worked out. But you could use V squared over R, or you could use I squared R. So V squared over R is really the only thing. If you can look at that, you'd clearly see that if I put 120 squared and divide it by 288, as in V squared over R, 120 squared divided by 288 gives me 50 watts. Check. Okay, so that's really me showing you that, yeah, these resistances are consistent with that power being that it has a 120 volts across it. Okay, so we got all that, and in fact our total power would be 150 watts. Okay, and I don't know why that's a W there, and so I mean a V there instead of W. All right, now let's look at the other side. The other side is going to be a little different because this 120 is going to break itself up to a small amount across there and twice as much there. So really you can think probably this is going to be 80 volts and this is going to be 40 volts. And this circuit's actually called a voltage divider. That's why I can do that really quickly in your head. You put 2 of those in series and you make this one like a rheostat or something where you can adjust it. And then you can set the voltage to whatever you want. It's just a common circuit item. So I suspect that's going to be the case. But we can go ahead and look at it and say, okay, well, what's the power for the 50 watt? Well, the power for the 50 watt is going to be the current going through it times the voltage across it, or it can be, which we don't know the current going through it yet, or it could be I squared times R. But what I do know is that R equivalent is equal to 288 ohms plus 144 ohms. So when I add those two numbers, you can see that I will get 432. Yeah, that looks right. Yeah, 432 ohms. Okay. So then I say V equals IR tells us that I would be 120 volts over 432 ohms. If I do that math, I will see that I is actually going to be equal to, and please check me on this, should be 277.7 milliamps. So let's see, 120. Make sure you put a 0 there. I didn't write it for some reason. 120 divided by parentheses. So just to check my math, I'm going to do 288 plus 144. And I get, yes, 277.7 milliamps, or 277.7 times 10 to the negative third amps. Those are both the same thing, right? So I now have how much current's going through there. And now I can calculate my P50. So my power 50 could be I squared times R. That's going to be 277.7 times 10 to the negative third, carrying an extra digit. That's going to be squared. And then, of course, that's the one that's 288 ohms. So if I take this number and square it and then multiply it by 288, I'll get 22.2 watts. That'll be 22.2 watts for the 50 ohm resistor. I mean, for the 50 watt light bulb. At P equals 100 watts, that's going to be 277.7 times 10 to the negative third amps squared times 144 ohms. That's going to give you 11.11 watts. So you can see, in fact, the 50 watt light bulb is actually going to be brighter than the 100 watt light bulb. If you wanted to calculate that, remember I told you since this is 120, that's twice the resistance of this one. So it should have twice the voltage across it than this one. So I said this one should be 80 and this one be 40. You can see that. You can say V for the 50 would equal I, which is 0.2777 times R, which is 288. And actually, it's exactly opposite that. It's actually, this one's going to be 80. That one's going to be 20. I was thinking of the currents. So I'm glad I actually checked this. 0.27777 times R, which is 288. That's going to give me about 80. It's 79.997. So that's 80 volts. And then the V equals 100 is exactly the opposite, as I told you, 0.2777. And that's 144. And you can see that one's going to be right at 40 volts. Okay. So what I was leaning towards is when you have two things in parallel like this, one's 100 and one's 50. This 100 is this 100 watts is going to have a lower resistance. Its resistance we found was what, 144? Yeah, a lower resistance. So, and that resistance is half the size of this resistance. That means that the current through this one should be twice as big as the current through that one. And if you actually check that, you would find that it does actually work. And that's what I was doing with this. Now the voltage is the opposite though. That's where your highest resistance gets your highest voltage, and your lowest resistance gets your lowest voltage. So that's where I screwed up on that. So it's actually good that I did the calculation so I could correct myself in real time, since I made another boneheaded stroke error. Any questions on that? Notice the total power in this case is what, 33.3 watts. whereas we got 150 on this one. So yeah, it's a lot brighter when you put them in parallel. Not only that, like I said, if they're incandescent lights, they're going to completely burn out. And in fact, some of the other types of lights burn out too. If you put them in series, then they make the whole circuit go dead. So, all right. That was example 6, I guess. So, and what time is it? It's already past time. All right, guys, I'll let you go. I'm sorry I ran over time. At least I caught that error. So I will see you guys next time. And I think someone, oh yeah, we already answered a question about lab. I'm waiting for the last person to leave and then I'll split. Have a good one. Thanks for coming. Sorry for botching that.
I have a question about the test.
Okay, yes.
I made a boneheaded problem.
Oh yeah, I saw your email.
Yeah.
Yeah, I have to think about what I'm going to do. Generally, our rule is that I don't do makeups, and you know, I sent emails out and all that stuff. I'll get back with you in a day or so. I need to think about this. If you know, I'm just going to look and see if anybody else did and that sort of thing, and just think about it. But I'll get back with you, William, on that.
All right. Yeah. I thought it was the same as the
You didn't even
homeworks
take
that
the
were
first one?
normally due on Mondays. So I thought, oh yeah, the test is also going to be on Monday.
Yeah. Yeah, remember, whenever I give you an online test, you should probably take one attempt like within the next couple hours before you forget it, so you at least have that one in the books. And I warned you all a lot about that. That's why I got to think about it. But like I said, I'm probably going to let you take it. Just keep an eye out for your email, William.
All right. I'll keep an eye out.
See ya.
Thank you.
Have a
Anybody?
good day.
You too, Clarence. Patrick, or that's the same William. Yeah, he's gone. Patrick, do you have a question, bud? All right. Well, I'll call it a day. Take care, everybody.